Okay, hi guys. This chapter, this subtopic, will introduce you guys to the HGL and EGL. What does it mean? Okay, basically when you are dealing with pump turbine, meaning that when you want to install, for example, a turbine. In a kampung where you don't have the electricity, okay, we prefer to represent our site visually to evaluate the possibility of that site, okay, and to be installed with turbine or pump using what we call here as hydraulic grid line and energy grid line, okay. So briefly, what is the difference? Okay, again, that this is for convenience purpose, the use of this EGL and HGL, so that you can directly visualize at a point. For example, here is your rumah, okay, there is your house there, and over here is a hill, okay, and you plan to, and there is a waterfall, okay, you plan to take the waterfall, you plan to use the waterfall to provide energy to your house here, okay. So when we want to think of that, we normally visualize that site like this, so that we know that at which part of that site along this line is having high energy or having lower energy. So at the higher energy, of course, you can install the turbine, and at the lower energy, you have to figure out something if it's significant, okay. So the difference between these two lines, first one is called the energy grid line, okay. Energy grid line is this solid line, okay. It's basically the whole energy that you can get from any point inside your inside along that line, okay. And the hydraulic grid line is the one that you disregard the dynamic head, which is the velocity effect, okay. So this energy grid line, if let's say you choose a point here, okay, at that point you will have the static pressure and the stagnation pressure, okay. But you don't an elevation head lah, but you don't take into account the dynamic head, okay. So it's just a matter of visualizing the potential energy from your flow, okay. So on conceptual part, if you are dealing with non-moving body such as lakes or reservoirs or static tanks, then the AGL and HGL coincide with each other, okay, because the only difference between EGL and HGL is the V square over 2G, this one. So if you don't have the movement, it's static, of course, it will be the same, okay. Yeah, this one is very clear. Your EGL is distance V square over 2G above the HGL. And then if in an ideal Bernoulli type, the EGL is horizontal like this, okay. This is an ideal condition where you have pipes, okay. The EGL is constant, but the HGL may different. Why is it different? Because for example, in between the two pipes, there is we call this as ventrimeter. You have ventrimeter, or maybe you have a connector attached between these two pipes, so your flow velocity will disturb. I mean, this kind of arrangement, configuration will disturb your flow velocity, okay. It can be slower, it can get higher the velocity, okay. So that's why the HGL line will change, but the EGL, of course, will maintain the same, because energy cannot be destroyed, okay. If let's say your velocity go down, there must be something else that is going that is increasing. So the EGL maintain constant. That is an ideal situation. Okay, and then for open channel flow, okay, what is open channel? Open channel in simple words is your longkang, okay, your drainage system, or your tunnel, water tunnel. Okay, that is open flow, which is most of the time not related with us for mechanical. That is for civil. Okay. The next thing is pipe exit. Okay. Again, when you have a pipe, when the end of the pipe, okay, the end of the pipe is drawn, I mean, looks like that, a solid line, not a curved line, then it means that the pipe is exiting to the ambient, to the atmospheric. So P there, P1 there is equal to P ATM, which is equal to P 0 kPa gauge. Okay. Similarly, if let's say your pipe intake, okay, it's a solid line like that, okay, then P2 there is equal to P ATM, which is equal to 0 kPa. Okay. The mechanical losses due to frictional losses between 2 points along a pipeline causes the EGL and HGL to slope down like this. This one is turbine. Okay, if you take a turbine between point 1 here, point 2 here, then your EGL will drop. If it's a pump, because you are increasing back the velocity, so the pressure increase back, so you will have an increment there. Okay. Okay, and again, as you can see in the figure there, you can observe a very steep increment or decrement of your EGL and EGL whenever it passes through devices, mechanical devices such as pump and turbine. Okay, and the last one is very clear. The gauge pressure of fluid is equal to 0 at a location where the HGL intersects the fluid. Okay, which means the pressure in flow section that lies above the HGL is negative, and the pressure in the section that lies below the HGL is positive. Okay. This one is actually related to this point. What does that mean? If let's say we take, you have a piping system, go down, okay, you are pumping, for example, you are pumping water from this side, okay, you go down, that is your second reservoir, this is A, that is B, so your flow is in that direction, okay. Your pipe is that way, okay, and then your water level is somewhere there. Okay, so what happened is your water hit the water surface, okay, and the pressure on top of the water surface is equal to 0 or maybe negative kilopascal depending on your atmospheric pressure. But down there, your EGL, that is your EGL. Down there, not EGL, sorry, your HGL. Down there, your fluid pressure is a positive pressure. Okay. Yeah. Okay, now we look into few cases, different cases when we have to apply the Bernoulli equation. Okay, again. When we are dealing with Bernoulli equation, the important thing is your choice of points. Okay, very important for you to know which points for you to choose to build your Bernoulli equations. Okay, for example, if you take this case, you have a gas tank, and then you taking the fuel, the gasoline inside the tank into another can. Okay, siphoning we call this. Okay, if we draw the schematic diagram, it's something like this. Okay, that is our first tank, and then you have the second tank. Okay, between these two tanks you have the pipe. Okay, that is the diagram. So here you have the water level, and here is your water level. Okay, so again, important things. Choose your points wisely. In this case, we can build the Bernoulli equation between the water surface there, point number 1, and the liquid surface there, which is point number 2, would be easier. So if we build the Bernoulli equation between these 2 points, okay, what will happen? That is our Bernoulli equation. Okay, and then any open surface, relatively big open surface in comparison to the diameter of your pipe, the velocity at that open surface is equal to 0 meter per second. Okay, just imagine that in your bathtub, if let's say you have a bathtub or your sink at home, okay, you pull water inside that bathtub. Okay, then first when you want to keep the water inside the bathtub, you have to close the outlet. Okay, so then you can increase the height of the water. Then when you open this part, okay, now you open that, what happened with the water? The water will flow. Okay, but what you see here on the water surface, the open surface, we call it as open surface, you are not observing the water flowing at the surface. Okay, it's flowing here, but at the surface it's not flowing. You can still see it's as a one line. Okay, even though it's moving actually. Okay, so that's why the velocity at any open surface liquid is approximately equal to 0 meter per second. There is movement, there is velocity, but very, very small. Okay, so it would be easier for any cases, choose the open surface as your point, because you know that at that point the velocity is equal to 0. Okay, same goes with the second part here. At your outlet, okay, the liquid will flow downward, okay, and fill the tank. But at that surface, open surface, you don't see the fluid is moving. Okay, only at that point there, exactly at the outlet of your pipe, the fluid is flowing, but on the open surface it's actually approximately 0. Okay, so that's why here from our Bernoulli equation, your V1 can be cancelled out. This is wrong point. I'm taking point 1 and point, that is point 1 here and point 2 there. So okay, this is a bit confusing because they are using 2 here actually to refer to point 3, because this one okay, so we build our equation. Okay, so to avoid confusion, because in this example, that example separates your point between 1, 3 and 3, 2. Okay, but here look at point 2 there is 0. Okay, so if let's say we take directly between 1 and 2, then you will have P1 over gamma V1 square over 2G Z1. We are not splitting our Bernoulli equation, okay? We take directly from point 1, point 2. Yeah, it's a bit confusing because this part is actually separating the points. Okay, now. So, this one becomes 0 and 0. To double check, see that one, V1 becomes 0, and here your V2 there become 0 as well. Okay, and then your P2 is open to atmosphere. It's not pressurized, so it's equal to P ATM. Okay. And then your P here in the gas tank, is it pressurized? No, it's closed, but it's not, maybe not pressurized. So you can cancel it out as well because it become PATM. Can be cancelled out. And Z1, Z2 depends. In this case, we follow the flow. Our Z1 is that level. Okay, and Z2 is here. Okay, yeah, it's a bit confusing, that diagram, but I hope you get the point there. Okay, when it's open surface, the velocity always equal to 0. The P always equal to PATM. Open surface, P equal to PATM, which is equal to 0 gauge. And then your V is equal to 0 meter per second. Okay, next, we look into this pitot tube. We did this in our previous video, so yeah, we skip that. But the point from this video, from this diagram is when your fluid hit a pitot tube or stagnation pitot tube, then your velocity at that point is equal to 0 meter per second. Okay, when your fluid hit stagnation point, which is the pitot tube surface, then it becomes 0 meter per second. Okay. This one also shows an example how you choose your points. If you have an open tank and then you have the outlet, so we choose the open surface as our starting point, and then our pipe there, outlet there, to be the exit point. Okay, so again, open surface, the P is equal to PATM. At the outlet also go to the ambient, go to the atmospheric, so can be cancelled out. And then velocity is open surface, approximately equal to 0. We can cancel out. V2 you cannot cancel out. Okay, it's flowing. Z2, that is our lowest point. It become 0, and Z1 maintain 5 meter. Okay, with that you can find your Z1. Similarly, if you have a hose, okay, and this is what we always do at home. Okay, when we wash our car, for example. Okay, so we take 2 points here, 1 point there, 1 point there. Maybe the objective of this is to measure the pressure at the hose outlet. Okay, so what you do, you can see you build the Bernoulli equation between point 1 and point 2, and then velocity 1, we can put it as approximately equal to 0. Okay, Z1 is the lowest point, equal to 0, and V2 is equal to 0 because that stopped, the flow stops there. Okay, so with that we know our pressure at that end of the hose. Okay, with that we are done with this part. Actually it shows the selection of points. Okay, very careful when you are selecting your points. Okay, then I will see you back in our video for one example. Okay, bye bye.